Hello everybody, welcome, how you all doing? Let's hear myself. Damn it. Right, chat only now. So now got that over there. Now today it's not scorching hot, so I can wear these headphones and enjoy the music with you guys. And hear myself as well, which is always an added benefit. Oh, okay. So unfortunately on Sunday we didn't stream, and I was ill. I had like a really bad fever. Like it was really bad. Um, yeah, so I was out of work Friday, Saturday. So Friday and Saturday I was just laying on the sofa. Sunday saw some family, but also laying on the sofa. And today I've just, or yesterday actually, Monday, I head was so cloudy still, but I managed to still go to work. Yeah, so today's pretty good. I haven't taken any paracetamol, and the sore throat appears to be gone. Um, and I don't feel. Yeah, I think it's just gone today, so it's all good. But yeah, it was a rough one. I've not had a fever in such a long time. But yeah, it's really bad. Hey there, Ransel. Hey there, not so red. Gonna get Vulkan tutorials using C, cause I really just like the C++ ones. Well, Ransel, you're looking right at it. We just go back and watch the VODs, Ransel. There's the tutorial. But yeah, I don't know. Vulkan's tutorial is all pretty pants because Vulkan is very complicated. Um, but doing anything more with proper like triangles and stuff, yeah, you'd have to do more work based off what we've been doing. But yeah, like in terms of like understanding the core way of interacting with Vulkan, the VODs go really well over that. It's just doing the whole graphics pipeline stuff is not covered, or render passes and stuff like that. But yeah, I've not got any good C tutorials. Not gonna lie. I think there's a few you can Google for. Good to get well soon. Thank you, thank you. So today's a really good day. So last stream, which was on Thursday, because I was ill on Sunday. I'm running over my power cable. Don't do this. Uh, oh. I don't want to ruin that. Oh, it was really bad. The fever was really bad. I was laying on the sofa. Hey there, Rohan. Yeah, just laying on the sofa. It was really bad. And thankfully, just recovered today. Like fully recovered. I feel like it was bad. Like I never I never thought I could just lay on the sofa, you know. But I figured out how. It was thanks to these buggers. Oh, well, no, the illness. I think I drank too many of these. Like I drank like 5 or 6 in on a Saturday, and 5 or 6 on the Sunday the next day, and I was just like caffeine, too much caffeine. So I think that was the thing. But yeah, it was a warm weekend, you know. Uh, Awesome, good stuff, Ransel. Yeah, that's not the best Vulcan stuff, but yeah, definitely have a play with it. Um, I know, but they're just so good. They're just so good. Mm. So last stream, we did this growable array called the stack, or called core stack, and it's amazing. Type safe, all written in C. It's using a new C23 feature, but it's completely type safe, and you can get the feature in Clang anyway through some extension. It's called typeof, right? There is typeof in GCC and Clang, so we're going to support that anyway. Yeah, it's a completely type safe stack. So in today's stream, we're going to be doing another collection, and it's called the hash table. So the hash table often gets overused by people because a hash table is not really always needed. It's a uh, like it's probably just, quite a lot of the time an array is just as performant as very small hash tables, and also the code is typically a lot more simple when it's just an array. So if you just have like, a handful of like entries that are going to go into this hash table, then you might as well just be using an array and just do a for loop over it and search for it the classical way. The hash table provides a speed improvement when the key to the so you have like a key and a value, and you want to find the value with a given key. Now in an array, that key is an index, right? And it's just a lookup. Whereas with a hash table, the key could be anything, and then you can get out a value of anything. So we're going to be doing a similar trick, but we want to talk about these hash tables and what they are first, and then we'll go over different implementations. Then we'll just get started on our one. Try soup. Yeah, I've had soup for a while. That's probably a good idea for the sore throat, isn't it? I'm here struggling with x86 instruction encoding. Oh boy. Well, why are you encoding the instructions? Do you want to figure out how that works as well? Yeah, that's why I was saying like just make your own assembly, because x86 is like, yeah, this is your rocket science, the encoding. And it changes all the time. You can change like one thing about an instruction, it's just completely different. I didn't touch grass for the past week. Oh no. Oh no. So for a hash table, I think let's just write out the interface, and then we'll start talking about like, so we can see kind of what's going on. So we're going to be having some form of like, we're going to be doing this thing again, right? We like this thing. Hash table. And hash table. So we'll get this a hash table T. So it's obviously not, well, should we do T? I think T might be a good idea. So what I'm thinking about planning on doing is bundling the key and the value together. So let's just pretend like imagine we'll have this thing called like, we'll call it like, we'll just call it entry. But yeah, usually it'd be like something entry, right? Where it's like, you just have some kind of thing that we're putting in here, and there'll be a key and a value. So maybe you have like a const char star name, and there's our key, and our value is going to be possibly, maybe you get back some integer. Very terrible use of a hash table, but there you go. Maybe you find, maybe you get like, okay, name and age. This classic example. So the idea is, I think we're going to make some form of like hash table of this egotist. Thank you so much. Thank you so much for the sub. Really appreciate it. Welcome back. Welcome back. What will be the hashing strategy? I've worked on XOR shift 120 algo in V8, which was used in math.random in JavaScript. Wow, interesting. Yeah, I think we might just do a dead simple hash function for now. Wait, is that a hash function you're talking about? Do you hash? Right. Right, yeah, it's just a hasher. Cool. Yeah, we're just probably gonna use fnv hash right now because it's dead simple just to throw in. But yeah, we'll be able to just swap it out with anything. So the idea is, I think with this interface, is you're just gonna say like the t type is gonna be the entry as a whole, and we'll get into why we're gonna do it this way. So in memory, they are gonna live like this. And then yeah, things didn't get benefited much better now. I recovered from my illness, which is super good. So you just define your hash table like this, right? Yeah, so you'd be using a hash table like that, basically. So let's write out some of the functions that we're using with a hash table, and then we'll explain exactly how one could be implemented, or how it's going to be used, how it can be implemented. So, yeah, so typically you want to find your entry, right? So I guess if you like void star, this would be like our void function we're going to make, like we did last time with the stack. So you basically want to find function, which means that I want to. It's like doing an array index, right? You're just that you're reading, right? It's just a read only thing, like you're finding it. But you don't want to modify. Wait a minute. Yeah. No. No, sorry, excuse me. I said that completely wrong. Yeah, so this one is like you want to find, but you don't want to insert into the hash table. So it means it can't necessarily early out, which you'll see in very soon. So basically, you're going to pass in your key, a pointer to the key. So the key in this case is name. Right, name is the key because it's the first field in this entry. Like the first field is the thing that will be the key, and you can kind of have as many values as you want in here after that with this design that we are going to be going with. But let's just, so you want to find with this key, and you'll get back a pointer that could be null, right? Yeah, it's interesting. It's like yeah, maybe let's return a null pointer if it doesn't exist. And then I think we'll need to have like some extra stuff passed in, like how big is the element capacity, and these fields are actually wrong. We need to sort these out. So let's like delete those. We'll fill in those in a bit. So you'll have like a void. So you have like a entry size, probably, I guess, passed in to say how big is this structure so it can do stuff inside, right? And then we'll need another one which is going to be called find or insert. And this one is going to find an entry with this key. And if it doesn't, it's going to find an insert slot for it. And then it will give you back a pointer to the entry, right? For this given key. So this is the basic idea of a hash table. You can pass in any, like, so you have a key which could be any type, and it gives you back a value. So how could you possibly provide a key of any type, including a string, right? And then possibly get back any value. So right. So it's kind of in the name. It's called a hash table for a reason. Because how it works is what will happen is it will hash the key and it will return you an integer. So why does it need to do that exactly? Will you show any type key on all the hash maps or configure each hash map to allow a configured key type? Yes. So it will be checked at it will be so hey there Temporus, the hash table, like the way we're going to write it, like we did this core stack one, right? And we've made it completely type safe, meaning all they'll have to do is pass in, like basically the way we do it is you have to call this like define stack with your type, right? So we do it here with these guys, yeah, and it defines a specific type. So we see we've got this T here. So say like of U32 data, right? Pointer. So what this means is when we can do some special magic where when we use this variable, when we use this stack variable in like this push one, for instance, it calls this push many. It can just do size of dereference data, and then it kind of is type safe, right? Like it just is type safe. From that point, so it won't just allow any like key to go in. Basically, we will have some checks in there. I think in this we might have some static asserts maybe, if to stop this from being a problem, perhaps. So we'll see about that. Yeah, we'll see how that goes. But yeah, we'll have to wait until we implement the thing first. So right, I think we need to start drawing this thing now. So basically you've got like so you take the key, you hash it and turn it into an integer. So when it's in an integer form, it means you can then either search for that hash and then find your entry, and then you can retrieve the value for that entry, right? So you can there's different ways these can be so I guess an example of hashing a string is just go over every byte and use a hash function, and it'll give you back an integer. Now, if you look at C, like one of the C++ implementations of a hash table, is actually like, and I think some of the Java ones are like this as well. I'm not quite sure on which ones are like this, but effectively you can imagine a hash table. So I think some of them bundle the key and the value next to each other, right? And they basically like, yeah, let's just do it like this. So imagine if they made a hash table and what you've gone and done is you said, I want to insert this entry here. Like with this key name. What it do a hash up. It will hash up that name and give you back some integer. And then internally there's like an array of these slots, and these slots can go under name. They probably get called like a hey there VMT. Get event tied. Moss Henry, chat. Yeah, how's things been? How you been? Yeah, it's been a while. Right, so typically you'll split it into like in like the internal and like some C++ library, they'll basically have an array of slots. And what it'll do is it'll take the number, say if the number's like 137, right? And you've got 1, 2, 3, 4, 5, 6, 7, 8 slots. Typically what they'll do is they'll just like mod it against that. Wait, how many slots did we say? We said let's 3, 6, 8. Okay, 8 slots. So you take like 137 and then they'll like mod it. Oh, I need some like science mode. They'll mod it with 8 or whatever. And that'll give you an index within this very limited array of slots, right? So then that one lands in 1, right? But then, like, okay, I want to pre-emphasize this again. This is what some implementations do, and it's not the best. So we're just going to explore this approach. So then what it's going to do is there'll be like a linked list of entries from here on out. So maybe there'll be a pointer, there'll be an entry here, and it'll check to see if maybe they'll have like a hash, they'll have like a key, and they'll have the value all sitting in like each of these slots, right? And then each of them will point to the next one, right? This is just some example of and they'll say like, oh, you got this hash key value again, right? And they can sort of like, well, yeah, and they will like, so they'll compare the hash, and if it's not a match, it goes to the next one, and then if it's a match, it might check the key, and then if the key matches as well, it'll give you back the value out the table. So this is not really good implementation. This is quite bad. One, because it's a linked list and you're jumping around. Two, like the hashes are not next to each other, so you have to jump. You can't just compare the hashes that are next to each other in RAM or anything. And every time you want to add something new, so say if you're trying to add this number in 100 and there's 137 for the hash, wouldn't it? So if this one was, these two are not that value, you'd have to allocate a new element, right? And then link that one again, right? So I think these are some implementations, or sometimes they give you, or sometimes they will like just have hashes that link together and the keys and values are stored in a separate array somewhere, and they will have a link to that array if it is correct or something like that. But there's many different versions of this. But and like it also, if you were to improve this approach, what you could say is each of these slots, there's a pre-allocated, right, number of entries that each of these point to. And this is an improvement because they can kind of be next to each other in memory, right? Imagine like a hash, key, and a value all sitting here in a way next to each other in memory. But okay, now just imagine if they're all hashes and they have like an index. Okay, let's give them the benefit of the doubt that it's even better, right? Where it's got like a hash and then an index to some other array somewhere that's larger than the slot array, that's far larger, it just keeps going on. And you basically, so you hash up your key, your name, you get 137, you mod it into the slot array, into these slots, which house many little entries, and you can sort of start searching through here for it. So you compare this one, is it matched 137? No. Is it matched 137? Yes, it is. Therefore, I'm going to use this index and then find my entry in this lovely array down here, and here has the key and the value, right? So this would be an improvement, as in this stuff will sit closer in memory, right? But it's still not the best, because it means that either this has to grow, okay, when you need more. Hello everyone, welcome. Thank you. Hello from YouTube. Oh, welcome, Omega Lol. Thank you. Very good. Doing some stuff off. Sorry, doing a lot of work stuff, cleaning up, preparing transfers to a new workstation. Very nice. Those are good times when you get that new workstation and it just zooms. Awesome. Should get to well in the weekend. Very cool. Yeah, nice. What happened to that link? Oh, it wasn't showing up on my phone. Strange. Yeah, we'd be doing like an FMV hash. And this is super overcomplicated, by the way. Namespace, class. Yeah. Oh, actually, no, it's not that bad. I've seen worse. Yeah, that's fine. Yeah. Yeah, I saw a scroll bar and I was like, oh boy, it's gonna keep going. But yeah, it's not so bad. The CPP way, exactly. Yeah. Those classes. Yeah, compile time stuff used for embedded systems where memory is limited. Fair play. Game engine is looking really sharp though. Keep it up. Thank you. The horizontal axis represents buckets here. Yes, buckets. Or slots, yep. So, yeah, these are the buckets or slots. Yeah, buckets. So, like, this is probably the best sort of version you can get going with this approach. The only problem is you have to either extend this when you run out of room in your bucket. With all your hashes in, or... No, sorry, no you don't. You just spill over into the next bucket. Yeah, and you use up their ones, or whatever it is, yeah. That's what you probably end up doing. Yeah, that's what you do. So you fix size this to like so many elements, and then when you fill it up, you'll just start filling up the next one, basically, of entries. So, but when you start doing it like this, you basically come to the realization is, why can't you just make this one big flat array, where all of your buckets are basically linear in memory? And then this problem just becomes a whole load simpler. You don't have two separate allocations here just for these guys, and then one allocation for each of these, right? Instead, what it comes down to is just have one big array where it's divided into two levels. There's basically buckets, and then within the buckets there are the entries in there, okay? So this, what's the benefit of this? And then to be the same size, ignore this thing which is not really proportioned too well. So the added benefit of this is everything is linear in memory, and say you get that hash 137 and you mod it into the buckets again, and you land in this bucket here in 1, right? You're going to start searching through that entry, then this entry, then that entry, then that entry. This one turns out these didn't match your hash, so then you can just go to the next one, and it doesn't mean you have to load anything more in cache, because chances are you'd have been loading it just by searching through anyway. So this is the approach we'll be going with, basically. But we are going to be having two separate arrays still. We're going to have an array of hashes, which are split into buckets, right? And we're going to have an array of keys and values, or AKA an entry. So we're going to have basically two parallel arrays where one of them is going to house these are the hashes, and these are the keys and values right down here. So what happens is when we eventually find our slot, say it's this guy here, it just knows the index, right? It would just been like, well, I am simply inside bucket number 1 in slot 4. But also it will know the global index anyway. So say if there's like 5 here, right? It's 5, 6, 7, 8, 9. It just knows it's in slot 9. So it just looks at slot 9, grabs the key value, gives it back to the user, right? So, and it doesn't even have to do anything special, it just calculates the offset of the address from the base address and returns. It doesn't have to access it at all. Actually, no, it might have to if it's an insert. That was a lie. No, we'll have to do a key check. Yep, that's true. Do a linked list. No linked list. Like unless it's to do with allocating memory, a linked list is basically always bad. Linked lists are the worst. One big array is by far simplest. There is virtually no performance hit until you get collisions. Yeah. So yeah. So I don't know, what else can I speak about? Has anyone any sort of questions they want asked about what is it in terms of like what is a hash table? I wonder if hip hop array, hip hop array, yeah. That's a good one. So what else can I go into about a hash table? And what's decent about, right? So we're also doing fixed sized hash tables. So a typical problem is when you fill up a hash table, like, because you have to do this searching thing, right? This search, when you do a hash table find, right? You basically, the only time you get to stop is when you find the value or when you find an empty slot, right? So if the hash table is full, you have to search over the whole table, and then like it will just keep going. Unless, I think there's maybe a trick you can do. But oh yeah, if you're trying to insert on a full table, yeah, it's just impossible. Like, you either have to find it or you have to insert it. Yeah, it's weird. Maybe. Yeah, so but the thing is, when you try and find your entry here, the biggest problem is you can just keep searching for a while until you actually find it if your hash table gets full. So to get around this, the idea is you want to allow for you want to make sure you size your hash table appropriately for how much you're actually going to be inserting in there at most, right? Because if you have an empty hash table and you have like one element in there, or not really one element in there, you have like a handful of elements in there, chances are you're just sort of like, where's a good example? Say if you have like, okay, say if you've inserted like this element here, or this element here, it's more practical, right? And you want to find a different value, different from the inserted one, just to see if it exists or not. So you do a find, and you land in this bucket here, the same bucket when you do your hash, and then you check to see if the hash is the same. No, it's not. Then you go here and you realize, oh, the slot is empty, so I can finish my search. But if the hash table is more full, with more entries, you would have to check over all of these different entries, that entry, this entry, right? So if you land in this one, you'll keep going. And then just to find out, oh, it's not in the hash table. So the more empty slots there are, the better. So the hash table is basically a trade-off between how much RAM can I waste, and like the more RAM I waste, the better speed I get, because you'll have more of these empty slots. And the whole point with this system where you split into buckets is that you can create those. There'll be a lot of low empty slots basically, because the buckets will be quite small. They'll only be like size of 8 or something like that. There's one interesting case of a hashed linked list, open chaining. Right, that sounds familiar. I forgot what that is though. Hey there, Samaric, welcome. Could you touch on what makes a good hash function, designing good hash functions? That's a whole topic of its own, and something I'm not really good at describing. But I think probably like the best way to explain it is you want say if you like feed in an array of bytes, right? Say if you feed in like a 1 and a 2 and a 3, these are like 3 distinctive different bytes that get fed into making something. Like this is a very low value. Like each of these is a very low value. So you don't want the hash function to change a tiny amount. You want the hash function to change a lot. Even so, like, so you can't just be so it can't just be like the hash function can't just be 1 plus 2 plus 3, because if not, you could get the same hash by doing 3 plus 2 plus 1, right? So you want the hash function to be very different, give you different hash depending on, even if the order is different basically. So there's tons of different things as well. Like you want to avoid collisions, like by testing many different common cases, right? But that's just a very quick overview that you have to do some research, and if people have some links, please drop them in the chat. Quick question, did you go to uni for computer science, self-taught? Kind of a bit of both. Went to college and then dropped out before I did the final year because it was, in my area, it wasn't too great. Raw libraries, basically zero. All of the system libraries, Vulkan, Windows, Linux, that's it. We do use some STB libraries for stuff, but that's about it. Right, anything else that we could cover about this? Yeah, I think let's just start implementing it now. But if people got any other questions, yeah, STB image, that sort of stuff. But yeah, we basically have, so the dependencies right now, let's just take a little bit of a gander. Third party, I got my custom C compiler. Right, I don't really, it's a dependency, so we use that for shader programming. And I've got I use B stack trace. This one is legendary. B stack trace, 400 lines, works across Windows, Linux, Mac, iOS, Android, because they're all basically the same, because they're all basically Unix. On Windows it's different, right? But so I have made a tweak to this myself, but it gives you a stack trace in C. So literally on the first day or two, we had stack traces where if the game crashed in any way, so asserts, aborts, even seg faults, we get a stack trace. So yeah, so it's super handy. Or even if there's a Vulkan error. Yeah. Right, what's this? It keeps saying link deleted on my phone. The perfect hash table. Right. Which one is this comparing? Is it going to say the Rust hash table? Because it isn't that great, actually. If they're still doing that C++, if they're still doing that Google one, it's still not, I don't think it's that good. Anyway, I can't bother to look at it. I'll look at it later. Thank you for that. Radio. So let's write ourselves an interface. So what we want to achieve. Oh yeah. So one thing I didn't mention, if your hash table resizes, you have to rehash things. This is something I wanted to mention. We're not doing this, but we will go over it. So basically, like, when you remember there's a mod operation, right? Well, so you get your hash, maybe it's 137, and you mod it with the number of buckets you've got, right? Then what happens is you find yourself a bucket, right? Bucket 1. But the problem is when you mod it with the number of buckets you have, like, you get a different value. You actually get a different value when you resize it. So even though the hash stays the same, when you mod it, it can end up in a different bucket. So typically, when you actually extend your hash table and make a new allocation, rather than just doing a memcopy, you have to do this thing called rehashing, which basically you go over every single entry in your hash table that exists, and you mod it again into the new hash table and write it into the correct place. And like, you basically reinsert it into the new hash table. But we're not doing that. So we don't have to rehash. But we are going to have a problem because of this. We're going to have a problem where we end up with lots of tombstones, which means when we do our find, we won't be able to early out. So when you remove stuff from a hash table, imagine you have this entry, and this entry, okay? Now there's a problem where if I remove this entry here, okay, and I'm going to give it a tombstone, right? But this doesn't mean we can early out in a find operation. It means you can early out in an insert, but not a find. So when you try and find, say if you land in this bucket again. Is this a match? No. Is this a match? No. Is this a match? Tombstone. Is this a match? No. Is this a match? No. Is this a match? Empty. I can get out. Now the reason why you can early out here is because you could be searching for these values and landed in this bucket, which means you have to sort of go over the dead entries, right? Now if you was trying to insert, you would still have to go over this tombstone to see if it's in the table because you're doing a find and insert. But you keep track of this slot being like, this is the best slot for it to go. And then when you find this empty slot, you go, oh, it's not on the table. But we're going to insert into this guy instead of this one because we get to reuse the tombstone and we'll get a better slot because it's earlier here. Now, the problem is when you go from a very full hash table to a very empty one, is there'll be tons of these tombstones, right? And they're just going to be a pain in the butt for your performance when it comes to finding an entry because they're just going to be holes. So what we're going to probably have to do is write a function where we just say call rehash or something like that, and just allow it to sort of like shuffle everything into a good position, like reinsert it into the buckets and put it in a nice position. So we can eliminate all these tombstones basically, and then go back to just having nice empty slots. But yeah, we'll have to add that in, but we will be doing that in the future, not now, because it's just an effort to think about. Unless we've got time today to do it, we'll start it. Our buckets in a linked list. No, that's in some other versions. We're not doing a linked list version. We're just doing a flat array version. Hey there, what's up? Hey there, Benotana. Good to see you. I don't really like the flat map from Google. Did a cool trick embedding control tombstone bits inside the key. Ooh. Embedding control / yeah, inside the key and using the SIMD key comparison. Oh no, yeah, but I don't think that's a good one because it's 7 bits, right? It's 7-bit hash, so you get a lot of yeah. So if we've got any extra time, we'll go into that. I don't know if that's actually that good because I actually implemented that myself, and I did some performance benchmarks against another one, against the STB one actually, and it really wasn't that good because there's issues with it which I could go into, I think. But if we got time, we'll do that. I just want to implement a hash table today, but I will. If we got time at the end, we'll go over it. So we need to remove as well. Remove a key. So initialize dnet. So you want to take in the allocator. You want to take in the allocator. Put it on an entry line as well in here. So yeah, I guess just a bit of interlude talk. I did try and SIMD hash tables before. I did some previous streams for past projects where I tried to SIMD hash tables, and basically I don't think it's good to use any SIMD operations on a hash table. Like I benchmarked the crap out of it, and I couldn't get a case where it was fast. I could get some cases where it's faster when the hash table is basically full, but if the hash table has nice empty slots on it, it's not faster because you're doing more comparisons than you need. But yeah. So you want to pass in some capacity. So the beauty is with this one, it doesn't have to be power of 2, like some hash tables, and you'll see why in a bit. Hey there, Wojilla, how's things going? Reduces locality of reference for. I'm not sure what that means. Locality of reference for trade-off of speed. But yeah, I just know like the Google one is made for Google. Google's problems for their data server. Like I don't think it's applicable to people's actual real-world applications. And I think the Rust people just blindly copied that one and didn't do any actual benchmarks on it. Well, maybe they did benchmarks since or compared to their one, but honestly, I compared an implementation of it against Sean Barrett's one, and his one was just way better, honestly. So my one is actually quite inspired by that one. I guess I can drop a link to it. So he's got one in here. Like this is what this is gonna be kind of inspired off of. It's gonna be different though, but it's just inspired by it, right? Making a multiplayer API for Game in Rust. Awesome. Yes, it's always interesting, the multiplayer stuff, doing networking, programming. I always want to do more of that. But yeah, I need some application for it. Yeah, it's good for perform default compared to the standard on map. You're right, Google tends to write more for the use case. Game tend to be different than network overlaps. Yeah, it's definitely better on an unordered map for sure. Right, but yeah. It's just when you watch that video that they did on CPPCon of it, they made it seem like it was just the best hash table for everybody, and it's generally not. So I can link to that as well. CPPCon, Google, hash map. Um, there's a video somewhere for it. I forgot. Where they go over it and how it works. Anyways, I can't. Anyway, have a search for it. Okay. Yeah. Yeah, CPP is the C preprocessor. Yeah. So I think we'll add another one and call it rehash. Right, it's gonna do nothing for a long time until we actually need it. Right? Until we actually do some performance stuff and we need to actually sort that out. Maybe we'll need an allocator in there as well. Right, because I'm gonna have to reallocate. I don't know. But we'll see. Hopefully we could do it in place. So rightio. I think that is the API. So what's the data look like? So we need an array of hashes. They're all going to come from one big allocation, by the way. We need an array of entries, but we just have two separate pointers just so we don't have to keep recalculating it all the time. We need a number of our entries count, our entries capacity, and we also need so we also need a hash function. How do we hash? No, wait. Yeah, how do we hash our entry? So we need to have type def. Yeah, so I think we'll say we'll return. Should we just do? I want a configurable hash. I don't know though, because sometimes you want a 32-bit hash, and sometimes you want a 64-bit hash, and maybe even higher, but very rarely, right? Because you can make a trade-off there. So we'll see if we can play around with that. So let's just make it return a U60. Well, you get away with it with a void pointer, don't you? So we'll see. Let's have a bit of a play. Core hash function, and maybe you pass like you're trying to say sort of like hash table hash function. You're taking the void pointer to the entry or the key or the entry. Something like that. And we'll return out a hash. Right. So we'll get the const right, okay. Now, you also want a key compare, right? Because sometimes you want a key compare, but sometimes you might be like, my hash function is the best. We don't need to do a key compare, and in that case, you'll just return true all the time. But sometimes, most of the time, you want to make sure that the keys actually match because you can have hash collisions, meaning two different keys can make the same hash. So you need an extra bit of safety in there. But the hash is the hash is there for pure because it's quicker to compare, right? So you're taking the entry A and B basically. Okay, now the problem is having a variable hash means the implementation might be pretty whack. Because you'll have if statements in different places where you say if hash 32. So maybe we just have separate functions for these. I'm not sure. Maybe you can have a 32 one, 64 one. Yeah, let's just do 64 only, maybe. For now. And if we need that speed improvement, we'll do something else. Alright, let's just roll with that. So these will get bundled in here. Yeah, we'll see what it's like when actually written the code. Let's make that change. Key compare. Should be called CSXCon, yeah. It's a shame C doesn't have a con. They should continue traditional of overleave verbose and call it. Oh yeah. C++ conference. Amazing. Rightio. So it's a little big, but does the job. So we'll have to declare a type-safe version of this hash table. And then we can start using that. So we'll have this entry called something entry. And then simply, T will go there so we can get the entry size. Bam. Oh, you have to pass in the hash size actually. Maybe. Interesting. Yes, maybe you can pass in the hash and the entry. Hash type and then the entry. Hash size. Yeah, I don't know. Right, so let's get implementing these guys. Define core hash table initialize. So this will just take in a hash table. Right, we're missing the super lovely key compares and hash things, right? You need to pass these in as well. So we'll do, what's your hash function you want? Very nice. What is your key compare function? So these guys actually will come in, right? Custom allocator, please. Capacity that we're going to allocate, hash function, key compare function, bam. So we'll call into this. Pass in all of these lovelies, plus the entry size, which will be size of, wait a minute, so this one needs to access the void version. So with the super lovely union, we can just do the address of void hash table. And that just gives the void version. So this gives us type safety from converting to this sort of like typeless version of the hash table. Gives us type safety here. And then we pass in all the stuff which is specific for this type. So hash table. So we want the dereference of hash table entries and get the size of that. So basically dereference of T star. So get you your entry. So the best thing about this solution as well is you can also make it a hash set, meaning that you can just have a key. You don't need a value. So you just deduplicate a key, basically. So that's another benefit of this approach as well that we're doing. Then we also need the align. So unfortunately, we have to do that silly dance here, but it's not a big deal. We have to use that new core core type of thing that we've got. So it's basically type of in C, but it's different on different compilers. Okay, dinit, similar sort of thing. So we're looking at like, we're just passing the allocator and all this size of information. Very nice. Now the find. This is where the fun begins. Let's get the new album on. It is time. What's the? Ah, we're still bright enough. That's good. So we're gonna do a find. So find takes in a key, and it gives you back an entry. Right, the entry that so we can do that type of thing, right, and get type safety, pure amazing type safety, by casting the result of the find to the entry, which would be super great. That. Now, that's cool. But what about the key? The key is a bit of a problem, isn't it? You'll just be able to pass in a void pointer. Or as CPPCon people like to call it, a void putter. So the problem is any pointer will just cast into that, and the key won't be safe anymore. Right, type safe anymore. And I don't think there's a way to actually fix it because we don't have the information about the key here. Actually thinking about it. So if your key is a const char star, you can accidentally pass in the const char star by value, which is a bit of a problem. But you know, maybe we should give you a value back. All right, here's what we're going to do. You pass in K and V, so maybe we don't have the entry in a single structure then. So you pass in K and V, as you would expect a hash table to actually work, right? KV. Maybe what we do is we do strut key, K key, and V value, right? And it's a pointer to that. Now you might be like, now you might be thinking, why didn't you put that in an actual type somewhere? But you kind of can't, right? And it doesn't matter because we just or will it matter? Because there's padding and stuff, isn't there? You have to know the size of key. Or probably offset of value. Really, offset of value. That's what you need to know. So we have to pass that in as well. Do you know what CMacro looked like a pain? Yeah, it was really good with the stack, but we're starting to find little holes here, but it can be fine. It's not too bad though. So I think what we can do, if we did it this way, so you can still do size of entry. Like you still do size of entry just fine, and a line of entry just fine. That's all good. But you need an entry size. You also need what's known as a value offset passed in, right? Because you need to be able to provide an offset and give them back the V for value, right? And you'll probably need a key size so you can mem copy the key when you do an insert. Yep. But thinking about it, so you might have like a key. So at the end we could say static assert, right? One of these lovelies. That type of key Wait, do they do... Can you do that? I swear I remember doing that before. Let's godbolt it. Call type of, it's basically just type of, but it's different on each platform. So, but yeah, I have to do core type of one now. Oh, you're saying should I use core type of? Yeah, I need to use that instead. Yeah, that's right. But yeah, for those who don't know, basically we have a wrapper around type of because it's different on compilers. So C23 just type of, but for Clang and GCC, it's that one. Oh, I didn't do a git pull. Actually, there's stuff to pull in. Oh, I'll do that later. See. Right, let's try this out. Static assert. Static assert. Type of int equal type of int. On a type of 1. Define type of type of. What do you say in GCC? Yeah, it's so great it's going to C23. They finally added it in. Definitely needed. Because it fixes their mistake with a line of as well, which is good. So now a line of doesn't need a line of expression, which is like the best. Well, it would have been the best if they had it earlier. Why is this an expected expression? I had this. It exists. Close that. Oh my days, compiler. Why is it? Wait, it's like a mine for a minute. Right, let's do that silly. It's not really T though, is it? To be honest, it's more like expression. Oh, maybe it's the fact that I'm doing right. You can't do this. That's what it's complaining about. Yeah, so I think there's an extension say is type. There's an extension to say like is type match. Yeah, that's what I'm looking for. Is something like that. Clang C check. But I don't know if we have that in any standard form. I think there is an extension like a GCC. Yeah, built-in types compatible. Oh, so I have to dig into. We'll have to dig into these guys if we want type safety. If we did it this way with a static assert, which is a shame. You could do size of, right? But then you're off. You know, if they're the same size, it's a bit weak, right? So that's the problem we have with the key. Is there a way around it? So we could define a type safe version as part of this, right? Be a bit hacky, but we can do it. We can instead define a special function that you call to get the type safety. So it'll be like, so instead what you'll do is you have to say hash table find underscore, and then whatever your thing is called, right? So we could, let's imagine if we didn't do the KV thing for a minute. Because we can get it all from here anyway. Wait, why did I want the KV thing? We wanted the KV separate, so we can maybe get the key type. That was it. Yeah, so let's undo that. Let's go back to having just T for entry. So the other way around it is by literally defining the more hard-coded version, the proper version of it like this. Okay, clearly amazing. Now what is, all right, so you need the K then. You still need K then actually. So K, this returns V. And then you would probably just do K underscore paste paste. Paste paste T. V. Right. So then this would just take, so you'd probably do static inline, and you'll probably just do, then this will return the void, you go against the void version, right? Where you don't have to care out the cast. Yep. And then you'll do like a hash table address of void hash table, and then you're passing the key void pointer, so it's just implicit. Then you'll do entry size, which will kind of just be size of hash table entries, and voila. It's basically what you'd have to do. So I think we can live with this approach. It's not too bad. Which just the usage is a bit different to the stack as well. But yeah, I think this will do. So let's put that KV thing back. So K colon V, or comma V rather. Okay, comma V. So right. So I think we got this interface nailed now. There's gonna be no more issues with this. And then we can get to that implementation. Radio. So we just got to do one for find or insert. Oh, wait. We forgot to do that super lovely structure, didn't we? K, key. V, value. Epic fail. All right. And okay. So find or insert, not OS, insert, there we go. So you find a key, if not, it's going to insert. Now we kind of want to know, we need a distinction here, right? So I think we might, see it's very hard to give back a nice return value here. Like we could, I didn't want to give back a Boolean as well. So unfortunately, we're going to have to do it via an out pointer, which is okay. So we'll say bool, and we'll say like is new out. So optionally you can take this, I guess, but the idea is if you inserted it, is new will be true. You can act on it. If not, do nothing. Very nice. Okay, so we can get rid of this one. So final insert is looking pretty good to me. Good. So remove. You don't really care about, void return, right? Oh, I didn't change that. Scary. Remove. So remove, you probably want a boolean to say, did it actually remove anything, So again, damn these T's. Yeah, that's it. So you just want to say, remove that key for me, please. This needs to be a boolean down here. And we're actually missing a key offset, because you want to return an offset to the. So these need entry size and a key offset for when it returns that pointer. So that'd be a super lovely offset of, right? When you have a structure KV KK V V what's the offset of V, right? So that gives you just a number of bytes. So here you meant to pass in type T, but we don't really have the type as a name, so we just make it up on the spot and just say, hey, give me what the offset would be for a structure like this. We pass that offset into this function here, so we'll be able to use that. We only need that for we need that for both of the finds, don't we? Okay. So that's looking pretty good. So when you remove you just need the entry size because there's nothing to do with the value. Nice. Rehash. So we don't have a rehash yet, but rehash is probably definitely going to take an entry size. So wait a minute, does the remove have to have any special? Yeah, it does because of the key. But the rehash can be like these guys. It doesn't need anything. You just need to say rehash. And you'll just need to take in that. And I can just call rehash void. And then you can just type in I want that like that. I don't know what we'll need really, but we'll just keep it there as a to-do. Excellent. Right, so we've got our super lovely interface now. So now's the time to implement this guy. It's gonna be legendary. Core C. Right. So, think about that hash thing in a bit. So like the stack, I want to have a nice little debugger set to say, hey, is this thing initialized? Because I feel that would be pretty handy. Right. So is this hash table initialized? So it will do this in debug, and it'll check it for us. So basically in everything but the initialize, we want this. So let's just put that in there. So we just want to put super lovely asserts everywhere so we don't just crash in the deep and have to look in the debugger. We just want to have it show up in the terminal. Bam, that was the problem. So we'll be doing probably lots of little asserts for that. Right, I'm just going to switch on the lights so we can see. Okay, so like the stack, we get a custom allocator in, but this time we're going to be allocating we're just going to be allocating one slab of memory, and the reason why we're going to be doing that is because we don't know what the allocator is underneath, and it could be, well, we could do two separate ones, right? But we don't know what the allocator is underneath. So it would just be better if it's just one big slab of memory, and then we can just free it. All in one go as well. So let's just work that out. So we just want to ideally work out the size that we're allocating. So basically it's like cap times size of U64, because that's our hash size. So that's how big, so that's our hashes size. Then our entries size is entry size times the entry size, right? So something that we do want to assert here, actually, just before we continue, is that we want to assert that we actually have a capacity that's non-zero. That'd be quite common, wouldn't it? Very easy to accidentally do that. We also want a non-zero hash function. We need a hash function. We need a key compare. We need a non-zero entry size, and we need a that's not possible to do. Really. Cool. So now what we want to do is make an overall size. So that is going to be like core int round up a line. So we're going to round up this one to the nearest alignment of whatever entry align is, because you've got to align our entries. Wait a minute, is that right? No, you stick the hashes at the end, because your entry is probably going to have, which one has the most alignment? Yeah, so you get the max align. Yeah, so I think you want to... Yeah, let's just do a little bit of waste. It shouldn't be so bad. So you pick your max align, so just be a line of U64, an entry align. So you get the max out of that. And that'll be what we allocate with. And then we can just align the... So the hashes can just come first. And then what we're going to do is allocate our data. So that'll just be core alloc, pass in the allocator, pass in the size, and the alignment is max align. And that's all of our data. So now we just need to populate all of the bells and whistles inside the hash table. So our hashes pointer is just the data pointer. Our entries pointer is basically this, right, in a way. So it's like core pointer add. We're adding from data. So this offs, is it an offset? Right. Oh no, we didn't do an add here. Plus entry size. Which means this here is the entries offset, which means that needs to be in a little local. Entries offset. So it's been a bit fiddly to do rather than doing just two separate allocations, but there you go. You're adding, so that'd be entries offset. Nice. So other than that, we've got entries count, so there's 0 in there. Oh. Entries capacity, that is cap. And then we just want to put in those two super lovely, the hash function and the key compare function. Right. Entry size, how's that unused? Oh, ho, 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 that was a bugger. There we go. So that will allocate ourselves our hash table. We'll never reallocate this guy. Then when we just dnet the thing, so I reckon what we want to do is like 0 this out at the end. So we'll just 0 everything like that. And then what I reckon we want to do is recalculate this again. Okay, so that'll just be hash table cap, entries cap. Then instead we're going to use dialog, and you pass in the hash table hashes pointer, because that's what we allocated, right? That's the base pointer of the allocation, and there you go. So that's basically it for that one. Now this is where the fun begins. Actually implementing the hash table logic. So very quick recap. What we're doing, remember, is we've got two allocations, right? You've got your hashes and you've got your entries. Okay, entries are a key and a value bundled together. You have an array of buckets, and inside each array of bucket there's a subarray of hashes in this case, and then a subarray of entries down here. And the idea is, so yeah, there's a subarray of hashes, but then for this one there's an exact same array down here. So whenever we find a hash that matches, we can just jump to the other array and go right in there without recalculating anything other than loading memory, and fish out and check to see if the key matches, and if that's true, return the value, right? So right, we'll be going over this as we type, I guess. Right. The first thing you need to do is hash the key. There's no way around it really, unless you've pre-hashed it somehow. Max align T. Max align T there's no point in max align T. Yeah, we'll probably end up just aligning to 8 bytes a lot of the time. I doubt we'll have any SIMD stuff in the hash tables. But yeah, max line t is the simplest solution. So first thing you want to do is take the hash table, use that hash function, and say, hey, can you hash my key for me, please? So this is where the name of it comes from, right? Key hash, we should call it really, right? Let's get that right. So hopefully we get time to actually test this out, and we'll be implementing this function later. So we'll just return. So you do your hash. So, you know, maybe just call it key hash. What is that being part init? Damn it. Let's sort that out. Okay, excellent. There we go, sort that out. Cool. So basically you just hash a key. So this would be a const key, I guess. Let's get the const correct, right? Const key, not doing anything with the key. Not doing anything with the key, are we? So, right, this will get you a hash back. Right, so again, we're not going to have an implementation of this just yet, but I don't know. I'm sure I was familiar with a hash function, like the FNV hash or something, right? Just takes in an array of bytes and gives you back some integer. So how do we get into these buckets and everything like this? So I don't know if you've seen some implementations, right? Okay. Yeah, so how do we work out what bucket we land in and start searching in from this hash? So remember when I said, you know, you mod it with something. Now the problem, you know, the mod can be deemed as like an expensive instruction, but I heard there's also some other benefits to using the AND operation as well. So an AND is like a cheaper way, so long as the number of buckets is a power of 2. Can we get away with using it? No, you might need a power of 2 actually. Because I was thinking with the capacity. Maybe. I think we write out first. We can always come back to it. So ideally what you would need is you want to essentially say bucket index that we search in will probably be hash. Yeah, so you get the number of buckets, bucket count. Isn't default ABL element long double 16? No, because max line T is that, isn't it? It is 16. defines the maximum alignment possible or something like that, even though 32 is actually possible. Bucket count, so we'll probably say hash table entries count. Now, so we have to get some constants for our buckets, basically. I might stick them in here. I have got an internal function header though. Should we stick them in there? Core hash table bucket entry count or entries count. So I think what we want to do is we want to stick the number of entries there are that we can fit in a cache line of hashes. So if we're going for 64s, yeah, this is why it's probably got to be hard coded as well. So we're going for 64-bit hashes. 8 of them fit in a cache line, so 8 times 8 is 64 bytes, and that's the size of a cache line. So you're going to be having, yeah. So it keeps it a constant, which means it can optimize it out when we do a divide here. So we divide this. See, I gotta have a think about this. Because maybe we want to round this up to the nearest entries count, right? Or maybe... yeah, maybe we round up to the nearest entries count. Or something else. We'll see. Yeah. Right, he says true for x86, but not. Yeah. I know maximum T is 16 on it, x86, but I'm not sure either. See, I guess we'll just mod it for now. Right, so just mod it. We'll see if we can improve that. So we mod it with a bucket count. How many buckets we got? This will be a bucket that we search in, that we start our search in. So basically the way the loop is going to go is we iterate over the bucket here. So you go over basically your, probably call it like an entry index. So we start on bucket index times by entries count or something like this. And then we want to like only stop. Well, so we want to stop at, yeah, maybe we, so index less than that, I guess. Yeah, we did that for range macro when we do that. Index 0, that thing, right? Okay. So what we're going to end up doing is probably making an entry index, which would just be index plus bucket index times by so we start on the base And then we want to end on... Yeah, this would just be better. Just do this, right? Okay. We're getting there now. So we just want to search over each of the entries in the bucket. When we finish with the bucket, we advance to the next one. Now, this also then needs to be modded against the number of buckets you have, because you could, like, you go outside of the buckets and you have to wrap around to the start of the table, right? Now there is an improvement you could do on this. You could basically skip buckets as you go. It's called probing, basically. No, not part of a competition at all. Not at all. You asked ChatGPT how to find locale issues with iStar. I explained the problem well, and then it recommended I use. I'm not sure if I get the problem you asked, actually. Yeah, so typically you can improve this. So after searching the first bucket, you can actually start skipping buckets. And you can basically have a step. This is something that needs to be played with. There's many different ways you can do this. But basically what you're saying is you're saying increase by step. And then you're saying like step plus equal 1. And the idea here is that like if you search through this bucket and you still got to go, well actually this in the next bucket by the looks of it, and you still have to go, what you're saying is rather than just search the next bucket, just skip to the one after that, and then if that one fails, skip 2 more after that, right? It's expanding quadratically, right? So so you just, so the reason why you'll do that, even though you might get some cache, you will get some cache issues, I imagine. Like, it could probably predict it and load it, I'm not sure. But the reason why you'll do that is because if you land in a different bucket, like you're not gonna, like, you know, when you insert and start in this bucket and put stuff in, and start and insert and put stuff in here, they will end up in as the table gets more full, as the buckets get more full, these two sort of searches won't all land in the same buckets, right? They'll go in different places. So ideally you could end up with better placement of your entries, basically. Oh, is upper. Right, I see now. I misread that. Oh, as if of 7 is true, then it must be lowercase. Right. Oh, sorry, yeah, not is upper. Right, gotcha. Oh my days, that's funny. That's funny. Wow. Did it really do that? That's insane. So this is a bit of improvement you can make it here. So the idea, right, is you're searching through the buckets. So what you need to do, see the hash is a void pointer right now, I think. Let's fix that. U64. See, it'd be nice if we can make that void, you know. And have different size ones, but I don't know how easy it would be. So you're basically going through here, right? Get your entry indexed. Okay, get your hash. So this is the entry hash. And if the entry hash is... Now, we've got to have some special values here, right? We've got to have two special values. So we'll put them in the internal code. I've really got to put them in the internal header actually, but we'll sort that out. Enum core hash table hash empty equals 0. Okay, hash entry. Probably want a tombstone one. These are little special values, and then you probably want to have like a user start. Okay. So what we need to do is when we make our hash, if the hash we get back is less than user start, we just need to add user start to it. So what we're saying here is we don't want the hash function to give us back an empty value or a tombstone value. And if it does, we'll just add it on and get around that. So that means what we can do now is we can say, right, switch on the entry hash. And if it's equal to that special core hash table empty, or that tombstone, we can then act on that. So for the tombstone, we don't care. We just care if it's really empty. For tombstone, we're just going to skip. So empty means, hey, we found an empty slot. We are just going to return null. We didn't find anything. Tombstone, we're just going to say, just carry on to the next one, keep going. But for default, we're actually going to check. We're going to say, right, if entry hash is equal to the hash, then we're going to be like, okay, I want to take a look at the entry. So now we need to fish out the entry. So for that, we're going to get a void pointer to the entry. And that would be the pointer add. We're going to go into hash table entries. Right, so we've found a match in this hashes array. But now we got the index for that, right? It's entry index, we got this. So we're just going to calculate the offset here into this array of entries. So we're just saying, building hash table from scratch, damn straight. Yeah. I've built quite a few hash tables from scratch. And I've done performance tests against many different ones. I've many failed experiments all my days. I thought, yeah. So we're just writing this one is basically based off Sean Barrett's one from STBDS. Just did it from memory. I've done many little variants off this one now. If I drop that in the chat again. That from my testing, that's one of the best hash tables that you can write. Is in terms of the speed on that one, it's pretty good. In many things, there's so many benchmarks against it. How long am I programming for? Programming for about 13, 14 years. Game dev for about 10 of those. But professional game dev for about 2 of those. Yeah, 2 years professionally. But hobby for 10 or more. Well, more than 10 actually. So now we've got the entry. pointer to the entry. We now want to use that super lovely, remember that other function we had in the hash table that we asked at the beginning? Key compare. So what we're doing is we're comparing two keys. The key, the entry, and the key that's passed in. Now if those two things match, we found ourselves a slot, so we just return the entry. No, don't return the entry, remember. We return the offset, because we only return the value. So we return the value offset from the entry to the value. And that will give a pointer to the value out to the user. If any of that fails, we just carry on and then go to the next entry. So that right there is what a find function basically looks like. Right. So we can put some comments, right? Keep searching. A value just got erased here. A value has been erased here, but our value can still exist past this point. And then this one is like, we found an empty slot. Ensuring that our value is not in this hash table. Thank you, programmer Prophet Cody. Appreciate it. If anyone has any questions about what's going on here, feel free, just ask away. And I'll happily expand more. So yeah, this is the basic idea of it. There's no entry size used. This is why unused parameter is the best error. Because it found a bug. Right. Entry index times by the size, people. We're adding in bytes here. So, so good. Right, so this is basically it. You know, if we tried to, yeah, we could. So if we were to make hashes, like, you know, change the hash, the size of the hash, and have like 32-bit hashes or whatever, we would probably have to make a whole separate function, because this, you want this to be guaranteed to be optimized and not have if statements everywhere, you know? What made you decide to do games with an engine? It's not typical to see, but I do see more and more who decide to write games from. Well, so typically I try and write little game engines or whatever, but I always find that. So I do a video going exactly over this project that I can link you to if you want to see a lot more of like what are the plans. You know, basically what we're planning doing with, like, you know, we've got like our own custom C compiler for shaders. What we're planning on doing in terms of Vulkan, right? What the plans there. I'll leave this in the chat if anyone's interested. But basically, I always found when you write a game engine, you're always writing so much code, like, because it's general, and you typically solve problems that you're not trying to solve right now. And what I want to try and do is like just write code which is specific for this game, and try that approach, because then it means we can cut a lot of corners. And I've always heard people suggest this approach, but I'm like, but don't you have to rewrite everything? But typically when you write like a game engine, you're not happy with the code 5 years later, have to rewrite it all anyway. And when you start from a project from scratch, if you're happy with your code, you can always just copy paste it over, refactor it, and then off you go. So yeah, I'm just trying out this approach, because I like trying out different approaches. Basically, that's how I typically find how whether an idea is good or not. I just have to try it out. Yeah, make games, not engines. So technically, we are still making the engine, right? We're doing these core bits and bobs. We've got we have done more already. We've got like a whole graphics GPU subsystem we've got, and it does run. Oh, I've got to run it from the terminal, you see. But so we have got 3 compute shaders running. We've got printf coming from a shader being dumped out to the terminal. Right, so we're printing from shaders here. 3 different compute shaders running. But we are just working on the core engine right now. And then after we've got the core engine in and we've got some keyboard input and stuff like that, all of that code that comes after is all custom for this game and very specific, right? Yeah, so that's what I was thinking. I could do power of 2. Well, also the entries in power of 2. Yeah, so this is that's like an optimization. And also, how slow is this in comparison to an and does it matter? Because most of the time is spent in here, isn't it, typically? I think the speed op is typically the speed optimization is typically waste more RAM, have more empty slots, right, and make sure you've rehashed it recently, right, that sort of thing. That's where the true optimization comes from. Not in the AND operation here, but possibly we do want to see if we can achieve that though. That's for sure, because it can help. I might have a question unrelated to your project possible. Can you recommend a cool C project to make? Oh, nice. Well, you can always make a nice little game or something if you're into sort of doing games. There is Raylib. Like check out Raylib. It's a nice entry level library where you can like put stuff on the screen and make little games. There's tons of little examples on how to use Raylib itself to do things. Start 2D obviously. So do some 2D stuff. And make little 2D. Make a little like 2D, a simple 2D game like Pong or something like that. But yeah, search for Raylib, give it a go. Yeah, just to learn C. That's how I used to do it before. Now Unity Unreal just adds more resource hogging. Right. That's how it used to be before. Yeah. Like Unity and Unreal are really big right now for people making games. Right, so what we're talking about is at high load factor, yes. Compared to linked lists, chains. Well, because you get the open address. See, I don't know about this open addressing thing. But yeah, the whole point is with this hash table is the trade-off is waste RAM and have like know the size is fixed size allocation. Meaning it never resize, no rehashing. Well, you could rehash it, but you won't resize enough at all. So the speed improvement purely comes from how many holes you have in the hash table. So it's a trade-off between RAM and speed. And that's the approach we're going to take with this hash table. I don't know if the linked list stuff is faster. Because the problem with the linked list stuff is I can see how you could probably link to the empty slots quicker in some cases, but you're just going to be it's linked listing, which means you're probably going all over the place, and that's far slower than going linearly through a bucket. Most of say the situation, been doing game development for about 4 years within engines, right? And as I go into the engine side of things, so naturally I'm curious about what I was doing in the space do. Yeah, you could go ahead and make an engine, but just write something specific for a game, and especially if you're starting if you're doing 2D, it's like definitely the approach to go. But yeah, right. I think we'll visit this power of two thing in a bit. I just want to see how the rest of these functions go, and then we'll reanalyze the code again. So let's just quickly double check. So we hash it. If it's a special one, go up. Make sure it's not 0 or 1. Make sure it's 2 or above. And then get the number of buckets. This divide is a constant, and it's a power of 2, so it goes into a shift. It'll be optimized into a shift, right? Then we mod that against the bucket count. Hopefully we can make that an and at some point. We'll see. Then we get the bucket start, get the bucket end, go over every entry in the bucket, get the hash. If the hash is empty, return early. Tombstone, keep going. If the hash is a match, fish out the entry, do a key compare, key matches, return the value. If it doesn't, keep going. When you finish the bucket, you go to the next bucket, mod it within the buckets. Again, we can hopefully avoid that mod there, right? Hopefully in the future. And you go to the next bucket and voila. There you go. When we see the goal, people run engine, they never finish it. Yeah. I don't know, the channel will probably finish his one, because his like using lots of libraries and such, but then it's like it loses character when you do that. He's using lots of off-the-shelf stuff. So typically you just get a very generic sort of engine again. And you're just recreating what other people have already done anyway. Yeah, so I meant not making an engine on its own, but making a game, writing an engine in bits, but that too. Yeah, awesome. You listen to any coding podcast? So there's the one by the B Scotch guys, right? Butterscotch Shenanigans. That's a good one. Even though I disagree with like a lot of the way they think in terms of like programming, like they have good takes and they're quite entertaining to listen to as well. They're pretty fun. But I like listening to people even though I disagree with them. That's completely fine. Also, if you know of Mr. Togglebit on here, there's wait, did you say program related? You did, yeah. So Mr. Togglebit has wait, what's this podcast called? I got it here. I like listening to it because I like hearing what he has to say about a lot of things. But it's called The Way of the Crab. Why has it got 2 B's? The people. This one. Yeah. So, like, apparently, like, there's two people and they're gonna be making a game, but they haven't got to making the game part yet. And if you're familiar with yeah, like I'm not sure who the other guy is, but you know, Hogglebit like streams on Twitch, so you can catch him out. It is gonna be in Rust and all that, but yeah, I like listening to this one. And every time I hear them mention the game, but then mention their other projects, it reminds me of one of the Simpsons episodes. I need to get the chat back up. Why did I close the chat? It reminds me of the Simpsons episodes where it's Simpsons, Millhouse. This one. You know, I'm just sitting there waiting for them to sort of like get to start making the game, and this is me. Yeah, this is it. That's it. That's me. Anyway, not sure if anyone's familiar with Simpsons, but yeah. When are they gonna get to the firework factory to start crying? Yeah, I hope to it'd be really interesting to get to that. Where's why am I failing to computer right now? Wait, yeah, that one. Yeah, there's a sort of podcast I listen to at the moment. There's not too many good programming ones. I've noticed. Anyone ever got any some programming podcasts that they listen to? I typically just listen to open source podcasts and that, right? X one Y equal if power of 2, right? This can work. Yes, that is true. That is true, Ryan. That's what we probably want to be doing. He's working up for several years too. Fair play. How do you learn about Linux and how it works? It's a very vague question, and it probably deserves a vague answer. Googling on the internet. If you Google for specific problems and just listen to yeah, TLB podcast. Back compilers. Ooh, interesting. Oh, it's got 5 episodes. Now, don't do them too often, which is a bit of a shame. But yeah, I'll take a look into it. Thank you. But John Blow recently finds his programming language very intriguing. Yeah, it's kind of interesting, but that's taking a long while, unfortunately. And it's probably going to be quite scrappy for a while as well. Like, I don't see... Anyway. Like, it's you know... I think John's made some like really good, interesting language advancements that other people haven't. And I think he's got a good mind for some of that stuff. I don't think he's got a good amount of time and effort to really put into a language which like he's got to somehow foster a community to help him get the language to where he wants to be, because it's a lot of effort and time, like to get all the bits and stuff around it together, you know. But yeah, saying that, I do really like it. I like his language mostly, above most of the new sort of languages that are out there as well. But I think John will happily leave his language very, like, you know, he's got very temporary operators in there and like very scruffy. You know, some of the design doesn't quite sort of work together. You know, and I think he'll quite happily leave it in that state for a good while, and maybe even stay like it for ages. And it's just got a very messy language that doesn't really sort of like work with each other. You know, this feature might not work with this feature. So yeah, I hope he gets that sorted out. But yeah, he's trying to make a game with it, so I don't think it's going to sort out for a while. Possibly there's been the same values for language like he does, if I recall it correctly. You mentioned trying to do an project, no success. Yeah, it's probably quite a hard thing to do, not gonna lie. Do you find Rust libraries as mature, not mature enough as the gaps building the web services, QoS and other things? Yeah, I guess Rust does have some gaps in some places, but for libraries. But again, it's like if I was to use Rust, which I did at some point, I'm not going to be writing libraries. You know, I'm just going to be writing the libraries myself. So like, libraries, like the operating system is the library that you need. That's it. Right. So how do we write the find or insert version of this? Dun 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 dun. So the idea is, if you got a tombstone, if you come across a tombstone, you go, I'll keep track of that. Tombstone index equal dun 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 U32 max. Alright, why am I doing U32s everywhere? Is this a good idea? Probably not. I can have a petabyte hash table. Let's just use the U pointers, right? What are we doing here? You putter. Right. Anyway, so we'll do this as like a U pointer max. We've got one of those things. We got one of those things. Why don't we have one of those things? Oh yeah. S64 max. S putter. Anyway, so you put a max. So what we're going to be saying is like, oh, you got a hash table. So sorry, got a found a tombstone. If this is not or is equal to, then this is equal to that. So we just keep track of the first tombstone that we find, so we can fill in those tombstones that we come across if we end up finding an empty slot. So this one is like, oh, we found an empty slot. We're going to be inserting. So we're going to return this time. Where's the out pointer? I didn't put it in the thing. Is new out. Or insert, right? Oh yeah. So is new out. So is new out is going to be true in this case, isn't it? And now we need to actually return the pointer. So what we're going to be doing is we're going to be saying we're going to be returning. So it's a pointer to the right. I think we're going to put a bit of a scope around here so we can do some magic. So the idea is we'll say like found. We'll say like you pointer, right, if is not equal to, we're going to say, right, that entry index is going to be equal to the tombstone one. Because remember, you might have had some tombstones here, right? You've modded into this bucket, you go over these guys, and you find an empty slot. But you don't want to just put the value here. You could do, but it's just better if you just stick it over one of these tombstones and just put a value in there. So that's what we're going to be doing here. And then we get the entry, we mem copy the key in there. Is that a good idea? Because you could have a string. Because the best thing about the entry thing is you could have a string that you search for to do a find, but you want the key. So you could have a string key And the string is temporarily allocated, but when you insert it, you might not properly allocate it. I don't think that's too much of a problem. So I think what we're going to do is we're just going to mem copy the key in there. So we kind of need a key size, to be honest. I forgot about that one. So key. So destination is at the entry because it's right at the start of the entry is the key, and we do need a key size. Then after that, we return core pointer add entry value offset. So we'll get that key size in there as well. Thank you so much, Pranzel. Oh no, you're talking about iron oxide. I've not seen that. Have you got a link? You like the way air handling is done for optionals, but like for game development. In game dev, the iteration speeds is extremely valuable, and the iteration speed in Rust is extremely low. Yeah, all those if statements and matches and everything like that, I don't like it either. I like the unsafety. It's great. Are you talking about my theme? I've always talking about his theme. Yeah, I like my theme. It's a custom theme. So we need the key size passed in as well. Just take another variable in, why not? The things you make me do. Why don't they get lowercase? Oh, dangerous. Size of k. Right, it's gone in there. No size of k. So that's cool. So what is the other case? So the other case is like you're not inserting, you've found. So in that case, it's here. So if you've found, you need to make sure you set this to false. Now, actually, maybe the person just doesn't care. So they might not want to actually have this thing. They might pass in null for that. So they don't really care about knowing if it's new, which is fine. So in this case, it's already been set up. It's already been inserted into before. So we just return the offset to that. Keep searching valid generators here, but still, yep. And we just keep doing the same thing. So I think that's basically it there. Right, so this key hash function, maybe we can make that better. Maybe we can. Yeah, we'll come back to this. Let's just do a remove quickly, and then we'll just start trying to use the thing, and we'll find the problems and fix it. So, how do we do a remove? So the remove is basically a find, right? So you do a find, and you're just gonna put a tombstone in there. So again, we'll just copy the code. You could probably just use a find and just do some internal magic on it, but I think we'll just inline it all. It's fine. So the idea is you want to found an empty slot, so the value doesn't actually exist. Tombstone, keep searching. We found a match and it's key match. Key compare. Then we want to return true, and we want to remove it. So how do we remove it? So what you need to do is you need to say hash table hashes. We need to say entry index equal that super special tombstone value. Thank you, Ransel. Appreciate it. Have you, because I did post it in the Discord, have you stolen it? Just take a look at it. If I use Rust, I do always use the unsafe asm. Like a just like, oh yeah. Yeah. Typically I'll just, yeah, do a lot of unsafe. Basically when I did Rust, I wrote my own standard library thing for a project, you know. So yeah, we just run a tombstone in there. Right, this is where the tombstones come from. And voila. So the final thing, you just keep going over until you find an empty slot. Excellent. So the final thing here is like, you know, it's going to do nothing, this rehash, but to do, essentially we want to reorganize the entries. Also, like reorganize / reinsert the entries into the hash table to eliminate the tombstones. Now, we could keep track of the number of tombstones by literally just upping that and upping a number here and decrementing a number. But yeah, something to think about. And maybe that could play into this. Like, don't rehash unless the tombstone count is, you know, there's a factor of, like, what is the ratio of tombstones versus the number of entries we have in the hash table or something like that. But anyway, something for another day. So this should be mostly fine. So we should start trying to use this thing and find what the problems are. One of my issues with it already is like, well, you have to write a very specific function to hash a key, whereas you could just hash bytes. No, I think that's gonna be fine. Let's try and implement it. So, right, let's get a standard hashing thing at the ready. So let's go and grab an FNV hash implementation. Pretty easy. There's one on Wikipedia, basically. Not Fallout New Vegas. Right. Pseudocode will do. Pretty easy to copy paste. So FNV hash is pretty decent for being quick. I think the Rust user by default in their standard library or whatever. It does suffer from having like probably more collisions than something that's like a more complicated hasher for sure. But the simplicity means that it's very quick to compute the hash. So it just has a trade-off is all. But this one's just really easy to implement, so we're just going to default to that for now, but we have the ability to swap this out whenever. So let's just write a hash function. Core FNV hash. Right. So this takes an array of bytes. So we've taken a void star, bytes, upointer size, and we might call this hash 64. I would kind of, yeah, let's do the 32 one as well. I so want to get like a 32 and a 64-bit hash table. I want to make that a thing. We could always return a 64 and never do 128s. And we could kind of do 16 hashes, maybe. Use 16 hashes with that. But then reading it might be different. Yeah, the read code will still have, yeah, require a bit of a think. So basically there's two constants. There's an offset bias, as they call it, and a prime. So the offset bias is what you initialize it with. Right, so you basically, we're going to call it a core FNV hash in it. So the hash initialize, and there's a prime. There's a sort of a thing you multiply with. So you kind of want to like 32 and a 64 of that, right? So they're in this super lovely table here, right? So basically you've got your prime. So the 32 one is that. This is the prime number. So 32 prime. Followed by the 32 offset bias. And then the 64 prime. And the 64 offset bias. So the initialize. So all your hashes, to be a legal FNV hash that you can compare against other applications, you have to initialize your hashes to that value. And if you don't, it's wrong. And every hash takes in a previous hash because you can combine, you can continue to hash on. You can hash different regions of memory to compute one hash at the end, right? You can initialize the hash to the initialization. You can have some bytes over here, bytes over there. So that will get hashed into one hash function, right? It's just, yes, you can call it multiple times to hash different things into one big hash. It's pretty decent. Another podcast. Ooh. Take a look. Two's Compliment. Whoa, what a name. These guys have got it. Let's take a look. Seems pretty low level. Ah, it's by Mr. Godbolt himself. Look at that. Very nice. Thank you. Right, let's throw an implementation in for these guys. Pretty easy. It's just a for loop. So basically you got your hash that comes in, you return hash. Ta-da! And you do a for loop over. So basically we should like cast bytes into a U8, right? And then we should do like a for range over every byte, right? So this is where FMV hash isn't too good because processors have like SIMD and you could process multiple bytes in a single thing. So, but this one's not compatible with SIMD because it's not compatible with SIMD because each byte, the way it works is the next byte is dependent on the previous byte's result, right? There's a dependency going throughout every iteration of this loop. So you have to be a different algorithm altogether. And imagine, like, I've never written a hash function, but I would love to have a play with basically taking FMV hash, writing up a whole bunch of tests, and just to test out how good this function is, and then modify it and write a SIMD version that writes, and just see what that's like, right? So you have your XOR with the byte of data. So the byte of data is B index, right? And then multiplied by the prime. So the prime in this case is the 32 one. So basically XOR equal, and then times equal. Alright, none of that silly pseudocode anymore. And voila, this is basically FNV hash gives you, it takes, to make sure I use a 64 one there. So yeah, the problem is like, see the hash is mutated and then used as part of the next one. So you can't, yeah, you can't SIMD this in any way because it just, the resolve of the previous byte impacts the next one. So, but yeah, it'll be interesting. Can you write a FNV inspired SIMD optimized hashing function? That would be interesting. Cool. So we can use this guy to now. So if we want to hash a key, so let's write a bunch of like hash functions that can work with this hash table. So we're going to write like a U64 core hash string. And this is going to hash a const char star. And then we also probably want to have like a key compare. You know, I'll stick on the bottom of this hash table. So just make some utility stuff. So this would be like a C string. You know, we probably want to use other of our own custom string as well. But so key compare. So you're a billion AB. And then what I think we want to do is just drop those in there. So you're just going to call. So the problem is the hash. It's as if like it's going to be hard coded to a certain hash function, isn't it? Like we could pass in a hash function. So we could pass in a hash function pointer. And this could basically be a pointer to one of these, right? And we'll be able to do whatever we want. But then you won't be able to do hash initialize unless what's some way we could do this? It's gonna be warm now. So another way we could do it is it just hashes the bytes itself. And you can have an initial hash that gets passed in. So what you're doing is passing in the hash function. Yeah, but then you can't write something specific. So yeah, I reckon maybe we could take in some like core hash function. 64 hash function, I guess. So if you were to do this, like imagine you have like a U64 hash. Like, okay, it starts off as 0 here, which is kind of wrong for FMV hash, but maybe it doesn't matter. And maybe you can say hash function string len. But then again, it's like you're hashing a string, so doing a string len is not ideal, but okay. So imagine you could do something like that. And then a compare would be like, you know, return compare AB equals 0. So ideally, maybe we can make some form of like general interface. So you could have like Yeah, oh, I want to strut. Return U64 core hash 64 function. And so that'd be the data pointer, your bytes, your size, and the initial hash you pass in. And you obviously do one for 32 as well. See, I'm not sure if we can do a 32 hash table unless it's a distinct difference, maybe. Something I want to look at. Right, so I think that'll be good. So this just needs to be part of that guy there. Which also means... What does it mean? Do I want another function pointer to say, hey, this is how you hash it? I don't know. Yeah, screw it, let's do it. Let's pass it in. So we want to like another one of these guys. Oh, I nearly missed that. Let's drop that in there. Got some ice cream and some crisps. That's right, crisps. Chips. It's a bit like calling pants your trousers. You know, sorry, trousers pants. Ah. Alright, let's copy this one in. Which means just null that there. Oh yeah. So this means when we call our key compare, no, our key hash, we're going to pass in what's stored into the hash table as well. Some hash function. Right, that'll be good. And on the remove, remember? Oh yeah. Alright. Alright. So hash function a to I plus a to I. What's so a to I is like string to integer, isn't it? Yeah, string to integer plus mod m for strings. I have no idea what that, like, what benefit does that bring? Where do you start banging my head against the walls? Yeah, you're being crazy. All that ice cream. What flavor ice cream you got? Which one is that? Because oh, such good ice cream out there. Is the music still going? It's still going. It's still going. Right. So should we start trying to use this thing? Oh, we didn't put the did we? Here we go. So. Oh, it's got to be a const. Const correct please. Are we missing out any other const corrects? For the see, find never mutates, does it? Find never mutates. Oh, we're not mutating the entry count, are we? Not that it matters. Oh, it does matter. It does matter. We didn't do a thing. So if you insert a new one, where is it? This one is new true. So what you want to do is say, right, hash table entries plus equal 1. Now, the problem is like, if you want to insert in your hash table is like got one element in it, it's not really good. Like, you could probably do some magic to find like, oh, I've gone all the way around. But when you start doing some different probing method, it's not like down here. It's not ideal. So probably the best thing to do is just say, like, okay, if the entries count plus 1 is greater than, it's got to be less than hash table is full and will hash table is full, something like that. And we just want to say like, we are about to use up the last empty slot. Just explicitly mention that so it's yeah, something like that. Regular vanilla. Of all the good flavors, just regular vanilla. That's cool. I like a good vanilla. Especially when you get that, you know, that fudge brownie, nice and warm, mixed with that cold ice cream. Oh, it's so good. So, obviously when you remove, right, and place in one of those tombstones, this number gets decreased. Right, so that's something we clearly forgot. Anyway, back to what I was... Oh, the mutating thing. Yes. So obviously find doesn't mutate. So for some reason you might have a const hash table. Just for some reason. There we go, just in case I ever have that. For some reason. Oh wait. This one. Right, anyway, there we go. So, now we can start using this thing. So, into the super lovely main function. Don't you go below 100% occupancy like 70%? Do you believe you fill up the hash table gets like... If you fill it up, the hash table gets exponentially more likely to get a conflict. Exactly. So our hash table is fixed. We never reallocate our hash table, which means when you use a hash table in this game, you have to make sure, like, you make the trade-off between how much RAM you use and like how fast you want the hash table to be versus how much space you're going to waste. So if like everything's fixed allocated in this game, everything. So we're not going to be like, so you always allocate for the maximum bound. And yeah. So yeah, the trade-off is literally size for speed. I know in regular hash tables that you see in like every programming language or whatever, when you reach like 70 or 80 whatever % occupancy, it will resize the hash table, rehash everything back into the new hash table. But we're not going to be doing that because I like my collections to be fixed allocated. So that's what we're going with in this project. Yeah. Hey, Joe Maker. How's things been? Good to see you. Right. So, super lovely hash table test. Hash table. Dun, dun, dun. So we are doing the key value in here. That was fine with it. Yeah, so the key is going to be const char star. But then we can't put it in there. It's const char star, can we? Bugger. See, I could have filled this information in and stored it in here and just had an entry, and then people just define a structure. Right, let's do another one in here where they can hash it as one of those sized strings at least that we've got. But what is it? Core string? Yeah, how many size strings we got? Because like, spugger. Yeah, I've got to think about whether I want this to be a structure or not. Yeah, we'll have a bit of a play. Let's just use this one though. I wanna. Right, let's get around the problem by doing this. Very similar. A size equal B size and data size. Whereas this one is data oh man, sad to see. I hope you're doing. I hope you get that stuff sorted out, Jim Mega. Yeah. You can bucket it. Keep each bucket at 70%. Ooh. Isn't that clever? Have the buckets at 70%. Now that is something I haven't heard of, and that is big brain stuff. Isn't that interesting? See, this is why I stream. Because we get good stuff like that pops up all the time. So, that's an interesting take. So it's like, hey, rather than just filling up the bucket and then going into the next bucket, we just stop at 70% and just be like, hey, just go to the next bucket and fill up their bucket. Pass it on. Interesting. No, I'm not being ironic. I haven't thought about it. I'm not. I promise, don't leave. Stay here and give me more good ideas. Right. So we'll just do the core string. So yeah, core string, and let's just get an integer back out, right? So we're probably gonna have a bit of a play and change this, but anyway, let's go. So core hash table initialize. So you pass in your super lovely hash table. Now you pass in all the bells and whistles. All the bells and whistles. So this is, they're a little bit extra to set up, and what 4 megabytes. That's fine. So we can use the linear allocator. So the capacity, again, we don't really know what we're doing with this, but let's just say it's 128. it'd be good to see. Maybe we can have the power of 2 restriction for the count, and maybe that can help out. Hash function. So that's going to be the core FNV hash 64. Then we want to do the core key hash string. And then we also want to do the core key compare string. Okay. So that will initialize our hash table. Now, we haven't declared one of these yet, so we're going to have to do that. So let's plop this here. We make that capital and we say core define hash table. And then you say key value, and well, bam. That defines yourself a hash table. Now, for some reason, I don't know why I scrolled from the top down to there. That was really dumb. Anyway, this is buggered. Buggered. Right, because I put a semi. But I want there to be a... Oh, okay, it can. Yes. Outside of function fix. Damn it. I want to just put a semicolon because it's neat. Offset of. The part of me just wants to just place something at the end so I can stick a semicolon there. But anyway, maybe we can think about that. Do I not have offset of? I don't need to include that. All these headers are probably really bad to include. Standard def, joys. We should not be including these headers everywhere. Anyway. Right. Within a type is a client extension? What? Is it ready? Oh, Leishko. Thank you so much for the sub. Really appreciate it. Welcome back. How you doing? A short version of allocator can't hurt you. Yeah, meanwhile, allocator. Oh yeah. Fill a bucket, double it, pass it on. Yeah, still better than alligator. That's right. Too many alligators. Oh, it's standard diff repeated. Thank you for being my extra set of eyes. Let's see. Yeah, so saying it's like a C extension, which I did not realize. But let's fix the other errors, and then it needs to be a const. Good old const. My favorite errors. Right. Oh, that's scratch space. What we're doing? Build, right? Scripts build. Let's do it. Oh. undeclared. Yeah, because you just declared it up. Oh, you didn't declare it up there. That's why. Right, I don't know if I want this key value thing separate. We could probably get away. Why do we need it separate? So we could do offset of, isn't it? Oh, is offset of a variable that you do against? Is that right? Oh, it's type, t-type. Because you do null casted into type. Yeah, that's the way they kind of work, isn't it, sometimes? Yeah, you can kind of, we could do our own version of this to get this to work. But the reason why is because we're an offset of to get v. Value offset, but we could just return the entry. Right, we could just return the entry as a whole. So why was we doing this again? Oh yeah, because we wanted the key as an actual right. So for type safety here, wasn't it? That was the reason why type safety on the key. Yes. Okay. So you can't declare the type. That's annoying. But if we declared our own type of, just for a bit, right? Let's do this, right? Define core. No, sorry, offset of, that's what I meant. Right. TV. Right, and we just do this. Null. Cast it into T star. Field. So that gets you on the address of that, right? Then you'll that casted into U pointer. And there you go. So let's try that instead. See what happens. Right, much better. That worked. So I've already never seen allocator short for allocator, only alloc. Yeah, that's cool. Yeah, I just made it up, obviously. But that's fine. Like, the problem with the word alloc is that it's short for allocate, right? But yeah. But anyway, if you look at it, it kind of looks like allocator anyway, so there you go. Yeah, it's okay to do stuff that other people don't do. That's still fine. Alright, what's the problem? Key has string. Right, these you might have to cast because they're specifically typed. Alloc A also conflicts with alloc naming convention. Yeah. Yeah. Yes, these have to cast, which is bloody annoying, but we might make that explicit on the user end just so they guarantee, because you're going from something which is unless, right, you make these void. So it'd be like const void. And when you're hashing again, const void. So I think that will be the way to go. And you basically get your string out. So you probably just want to call it key as it comes in, right? And then that way, there's no casting going on in the user sort of like API. Just in the function here, basically. So it's like a core string star string equal a. Oh, wait. Wrong one. Wait a minute. String key const A string B string. Oh, why am I typing string so wrong every time? So I think we might need like a string B string here. This is const char star. Let's call it string key. A string B string. Voids. Const void. Right, so those should be compatible. Just gotta make sure this is all right with this key compare function. There we go. So now when we look at it here in the mains, no errors, right? Awesome. Okay. So the plan is from now, let's try it out. So let's get a couple of strings on the stack here. So do a core string. And I'm going to say like A. And we'll call it, let's just make it core stringlet. This one's going to be like test. The other one's going to be like another. Let's call it programming or whatever, right? So we're like 3 strings here, and we'll store some values in with those. So let's just punch 3 of these in, right? Hash table, insert, and we use the insert core string u64 function that we got. This takes in that hash table, then takes in a key that we want to insert. So we want to insert address of A. So we can already take it in, we can actually insert it by value now, rather than taking an address, because the address is going to be a bit annoying when a key is typically just kind of a value type, right? So why pass it in by value, by a pointer? Because otherwise you have to put it on the stack, and then we can just put it all in line, and then we'll take the address here instead, and then hopefully the compiler can sort that one out. So I think that will be pretty decent. Change. Now, so all we need to do is pass in A. Now, you kind of want to know if it's new or not, but we'll just pass in null here to avoid that. Then we're going to dereference it and then assign 1, 2, 3. Right, 1, 2, 3. Do another one. We're inserting B. 4, 5, 6. C. 7, 8, 9. Right, so we're storing those values in the hash table associated to those strings. So now what we can do is we can do a print, and we can print out the string and its value. And then what we're going to do is say, right, just print out a.data with the result of whatever this is. So the result is going to be just defined. And, hopefully it finds it doesn't crash. Just give it a go. And then hopefully gives us the right value out, So let's try that. A. Oh, come on. Wait, we've got arguments? KB. Oh, sorry, ZU. Right, B, then C, C, then B. Right, nice. So this is a nice test. We'll be able to see if it works or not. Also had company dev experience about a week ago. We have had some very nice talks, which I of course can't talk about a lot of stuff. But I have one talk I've learnt something interesting. Well, about 1 out of 7 people is neurodivergent in the gaming industry. About 1 in 5 would mean that my company is around. Right. Right, so okay. Fair play. I don't have anything special, but it's a ton of boxes for having both autism and ADHD. Yeah. Yeah, you see, I don't know. When I was younger, they said I had I struggle with reading, right? Whenever I see any big block of text, it just, I just shy away from it. But I do come back and sometimes read it, and um, it's taken me a while to learn reading well, and just English in general, like the language. I had to sort of learn it like logically, take a different, because my brain will, supposedly works differently. But then again, I don't think it's really good. I think it's maybe okay to recognize that this person maybe thinks differently, but I don't think it's good to sort of um, like, uh, make excuses for the reason why you're bad at English or bad at doing. I think identifying why you're bad is fine, but I think these sort of categories that people sort of discover and the way they react when they find out their child has this problem, they start to make it seem like they're incapable at doing many things, but really they're super capable, but they just think differently. You know what I mean? And there is a spectrum of it. Obviously, some people are really incapable at doing certain things, but some people just have a different way of thinking. And I don't think I think these boxes they can be useful, but I think they can be quite dangerous as well at the same time. Neurospicy. Oh yeah. Hey there very much. How you doing? Since there is a big genetic component, a lot of people only figure out they are neurodivergent because their kid is. Right. For me, jumping letters frequently B and D's, yeah, interchanges, I get you. Yeah, P's and B's, those as well. Yeah, like it's I found it really hard to especially when I was at school doing English, really hard. But yeah, I think it just means that they require different way of thinking about it as well. Because some people just don't get it. Like, I didn't get it. Like, where does the semicolon go? Yeah, not doing good, Renatomp. Yeah, doing good. Yeah, programming C mostly. C is the way. Right, does it work? Segfault. No, it doesn't. Segfault? In my Linuxes? What is going on? 65? What? What do we do? Huh, right here. We dereferenced an old pointer. That's not good. So let's have a bit of a play. But don't because it's disorder anymore because everyone's learned from me. This is just that. Right. What are we trying to do? Okay, I'm just gonna go and get a quick drink, and we'll sort this problem out. Okay, enjoy the tunes. Perfect. Right, welcome back, everybody. All right, there we go. So, why does it crash? That's a good question. So, I guess we can just follow it through, right? Core breakpoint. Right, so let's drop that in there. Hit the breakpoint, bam. So let's see what happens. Right, that's a bit annoying. It calls into there, but it's a one-liner, so you can just skip it. Right, so we get this hash. Yeah. That's fine. Get your bucket. 16 buckets, please. And on bucket 4, empty is new. Times the entry size. You memcopy the key in there. Do you memcopy key size? Did we put the right? What's the key size? Did we do that right? It should be 16, right? Oh yeah. So that goes in there just fine. Then you add to the pointer. Should be good. So we do 2 more. I can't be bothered to check them, but let's look at this one. So if we remember, yeah, bucket 4, good. So look, get the first hash, right? 0. We didn't insert the hash in. Okay, so it's failing because the hash is 0, empty slot still. So it's probably just overwriting the same slot each time. Right. So when we insert, we obviously didn't do this. So if it's new, you also need to say, oh, see, we did it for the remove, but we didn't do it for the hashes entry index equal hash. Ta-da! And wait, I hit the breakpoint. That was one line of it possibly working first time. Let's see. Right, here we go. There we go. Yay, it works. Right, there's a hash table. Ta-da! But there's some interesting ideas we've heard in the chat, and I want to explore them. So let's take a look at some of these interesting ideas, because we can make this even better. We should test the remove out, shouldn't we? Should we test the remove? So let's say the remove is going to work, surely. I don't know if we land in the same bucket or not, so should we do some printing? Let's see if we land in the same bucket at any time, and then we can kind of do some check. ZU. So 4, 3. Damn it. Right, so they're in different buckets. We could hard code a bucket. Nah, I ain't bothered doing that. But yeah, the remove is probably going to be fine. We can just follow it through and just double check it actually. Let's do that. So let's remove the one we just put in. Right, let's watch it crash first. And then we'll do a... So it crashes. Right, couldn't find it. It found test and another, but didn't find the other one. So this line crashed. Let's chuck a core breakpoint in there. And then what we're going to do is just get there and just follow it through so we have a bit of a check, see what goes on. So, you know, it does the hash, gets us our bucket, finds the entry. Is it a match? Yes. Does the key match? Yes. Stores the tombstone in there. It does nothing with the key because it just needs to overwrite the tombstone is all. And then we decrement the entries count down to 2. Okay. Then it returns true. That's good. That'll work. Okay. So how can we make this thing better from this? What things don't we like? What things do you think we can improve? Mm-hmm. Oh, right. What to do now? What to do? So how can we make this thing better? So like, one benefit of this... No, it is a benefit, isn't it? You don't have to define an entry type, meaning you can just do key value and that's fine. Yeah, I think that's a pro. It is a pro, isn't it? Right, I think the interface is kind of fine. Using it, you know, has a bit of, you have to define some things up front, like these sort of like hash a key function for me, and also compare the key for me, please. Right, you have to do this up front. Bit of a pain. And what else do you have to do? Yeah, so you pass them in there. So that's a bit of pain setting it up. But yeah, when it's set up, it's quite... You then have to use this special thing so you can get a type safe key argument. It's okay. I don't think we're going to be having tons and tons of hash tables anyway, just a few, so it should be fine. Even on a find as well, you have to do it. Well, you don't have to, you could use the void one, but yeah, type safety. We get it. Okay. But there was a really interesting... Now I want to find the person who suggested this. It was so far up now. Laurie Master, there we go. He was saying the biggest problem with this implementation is the fact that basically... Wait a minute. Keep each bucket at 70%. Would they even work? Let's go over it. He was saying the problem is like, save your insert into this bucket. You got an empty slot, so then you just put one in there. Let's say you insert a second thing into there. So you scan over this one. You scan over this one, find out it's not got the same hash. Go to the next one. It's empty. Put it in. Then what it's saying is like, you want to keep 70% in each bucket. But then if you keep 70% in each bucket, surely that you're not going to make an insert slot anyway, so I don't think it will work. Because if you keep 70% in each... Yeah, I don't think that's going to work actually. It sounded like a genius idea. But I don't think it works. Because say if you fill in that slot, and then fill in that slot, you keep this one free. The problem... Yeah, we need more arrows. Can you see? There's more arrows, I swear. The problem is that, like... Yeah, you would hit this one and be like... the whole point of finding an empty slot is saying that there could possibly be no more entries after this one. But if you're going to go and insert something into this bucket, you would go, okay, not that one, not a match, not a match, not a match. Empty, I'm going to leave, right? Oh, sorry, empty, I'm going to put one here, because we're trying to insert, that's what I meant. But then, if you want to keep this one empty, like literally empty for some reason, you'd have to put it in the next bucket, so you'll put it here, right, if the slot was empty. But then when you do a find in the future, for that one you've just inserted, you'll go, not that one, not that one, not that one, not this one, empty. Now here you'd usually return because it's an empty slot, but then actually you insert it afterwards. So I don't think there's a way of doing that 70% thing. Doesn't seem sensible. Sounded cool though. It's called load factor, then it would rehash. Right. Since you keep the count, before the bucket would have space. Not really, because the buckets each have their own count. You'd have to have a per bucket count. Why would it skip the first 4 slots? It would ignore the first 4 slots if they are not a match. If they're a match, it will overwrite it, right? The idea might have been if your hash map is 70% full, you create a new one. That would change the end of the current one. Yeah, I'm not chaining or create a new one or rehashing. Yeah, we're not doing, because otherwise you have to reallocate and copy and whatever. Right. So the other idea is to make it power of 2 and then avoid modding, because we are actually modding when we skip a bucket. Sorry, when we change a bucket, we mod it. And we mod it here as well. So maybe anding, doing an and instead is better, right? Since you keep your, yeah, it's not quite. I'll keep the idea in mind and see if I can think about how it could work. But yeah, because the problem is like if you fill it up. Yeah, I don't think that's gonna work. Where's the music? Is it still going? Still going. Still going. It's just too warm for me to wear these headphones. Another way of doing it is a linear hash map. Small chance of collisions. If you have one, you use the next slot, which would normally map to another hash. We have a linear hash map, though. But you're talking about not having buckets. Just make a linear array and mod into the array. Right. Yeah. Okay. Then if you have one, use the next slot, which would normally be into another hash. Yeah. So yeah, we could mod into the yeah into we could still have buckets, but we could mod midway into a bucket. That's another way of doing it. By consistently hashing, use the linear array to define partitions. I think Google Hash Map is linear 1. It's basically the fastest hash map around. I don't know if that's true. They said it was the fastest hash map, but I don't think that's true. I actually implemented it and I compared it against other hash tables, and it generally it was not fast. Like I think I think it's fast for their problem. Yeah. Like I've tried SIMD on a hash table as well, like trying to SIMD a hash table, and I found out that SIMD didn't really help out from my own tests. So I don't know. Let me know if someone's done otherwise. But yeah, I think the Google hash table is good when you've got quite a lot of buckets with filled data. It's really good at having high load factors, basically, compared to other hash tables. But I don't think. But I think you get quite a lot of hash collisions because they do a 7-bit hash. Yeah, it's called the Swiss table. Yeah, I know what it is. Yeah. They use a 7-bit hash and then they have a big hash. And they do the SIMD over the small 7-bit hash. But there's so many collisions that could happen there, you're basically going to be bound to check the bigger hash anyway. Like, it's just doing too much stuff. It's doing too many extra compares. I doubt they get to skip over a large amount. Just in the next slots is also dangerous. They tend to be pretty long runs. I think with long jumps of a prime number or triangle numbers is usually better. It's a 2-part hash. Yeah, they have 2 hashes, right? Yeah, so we could mod. So we could mod into just a linear array and mod halfway into a bucket. And then just continue from there. Maybe. 7-bit segment is there to be able to SIMD it. Yeah, I know, but you get a lot of collisions, right? You get a lot of 7-bit collisions. So if you mod it into the bucket, right? Maybe I need to redraw this, but yeah, you see, if you mod it into the bucket or into the whole tape thing as a whole, you can maybe search the rest of the bucket, and then that way you're less likely to hit the same bucket. Which means the first thing is more likely to be more sparse, right? And then you'll just search from there, and then you can always do the jumps past the buckets anyway, right? That's interesting. Maybe it might be interesting to make the step 2 by default, I'm not sure. Yeah, we need more arrows. I just need more arrows. All the arrows. On one hand, yeah, in general, if you have those 128 buckets, you have many more in bucket collisions. Yeah, I'm not doing a linked list. Linked list is not great. So then we could do like a power of 2 capacity, and then you can and that, but then you can't really and unless you have a power 2 number of buckets. So you round up your capacity to the nearest power of 2 buckets. So you turn it into a bucket count, round up to nearest power of 2, turn that into a capacity. Yeah, maybe let's just do that first. Let's just do that now. That's quite easy. Because then we can change it into an and that's an easy win, at least. So the idea is this is like, this will get changed, right? So I think we have like a nearest power 2, right? Do not round up power 2. Let's do that. Let's get one then. Power of 2. There's some little bit tricks you can do just to do it. Yeah, it's use CLZ, isn't it? Count trading zeros. And you just shift it. Hmm. Yeah, I don't think these are good. There's one with like CLZ or something. I always forget which one it is. I do have an intrinsic for that though. Right, least significant bit. Wait, you want most significant bit index? That's it. Most significant bit index. So that uses count leading or trading zeros. I forget which one. Just an internal function we have. Bear in mind, it's probably in my maths library. Scalar, something like that. U64 ought to do it. So we're doing bit LSB, most significant bit. So that gets you the most significant bit set. Then you do that plus 1, right? So if this is equal to 0, but you don't want it to be 0. It's never 0 because it's not done here. So if you do the plus 1, 1 shift left that, right? So this gets you the next power of 2. Because if you have the bits in an integer, when you get the bit index, the most significant bit set, the index to that will be, so if we get up in the calculator, it'd be easy to, bit of a show, wouldn't it? So here's the numerical system, right? Say we have these two bits set here, 10,024, right? You get the most significant bit index, so it searches from here and gets you it. It's an intrinsic, so it's quick. So it's bit 13, right? So all we do is we say, okay, we'll add 1 to 13, do 1 shift left 13, and then 14. And there it is. So there's your next power of 2. So we kind of like maybe want to put that in a super nice, it must be non-zero, but maybe, so define core in roundup power of 2. I. Now you want to make sure, so if I is equal to 0, then it's just 1, else this thing. Okay. Now, round down, you can basically do the same trick. Round down power of 2 though, like, I guess we'll just put 0. But you want to do like, you just don't do the plus 1, right? And there's it done, right? So there you go. Cool. Unsigned, yeah. Unsigned integers. Yep. Right. Power of 2 versus prime, on the other hand, is a trade-off between a faster bucket index creation versus less collisions. But yeah, I heard the mod. Yeah, I've also heard that the AND operator is just better than a mod if you used to compare it with something that's not a prime, right? Mod is very fast on modern CPUs. Divide these days, even Zen are pretty much 2 cycles, right? That's interesting. Yeah, but what I've heard though is that the if you was to use an AND operation versus a mod for specifically for hash tables, that the AND will give you less collisions if it's a non-prime that you're comparing it against, right? Is that true? I'm not sure if that's true or not. So what we're looking at doing is doing like a cap divided by that bucket thing, wasn't it? Bucket entries. Then you want to like... So you kind of want to make sure that is like number of buckets. You kind of want to make sure that's a non-zero. And then you want to round that up to the next power 2. and then you want to say, well, cap equals, might be wrong, before I've seen prime count seems to be the optimal for bucket counts for hash tables. Yeah, I wasn't really saying that's wrong, because I think that's correct. What I'm saying is like the mod yields, like if it wasn't a prime, the mod is not as good as the and. But I could be wrong. That's just something I've read on the internet that I don't know anything about. So anyway. Right, so this means that so now we know that this is a power of 2. Right, buckets count is always a power of 2 now. So we could assert it, right? We have an assertion here. Debug assert is power of 2, excellent. So we should have asserted that. So anytime we make this now, we just want to do a nice little check. So now we know that it's a power of 2. We can do a nice little check. So we can just do and of this take 1. And then we can do it in here as well. Let's give that a go. Yes, because the low prime number density as we approach plus v infinity. Yeah, primes would probably be better. But then I have to have like a prime table, wouldn't I, to look up the nearest prime. Let's just go with this approach. Right, anything else that was outstanding to look at on this one? This, can we maybe think of, right, it still works, that's good. If power of 2 really depends on the most of your hash entropy in the loop. Most of the entropy being in the lower bits. Right, that's interesting. Yeah, depending on the... It does, doesn't it? Because you're just anding it with like... Depending on how big your table is. So... Yeah, I should have a play with that. When we got something working, it'd be interesting. So maybe convert that back and to see how it compares with a mod, you know? So I'll put to do, I'll leave it to do in here. To do compare with mod. When we have something. Something like that. Right, is there anything we can do to solve this sort of like... So if you fill up the hash table... you're going to have to do this rehash. Yeah, so you fill up the hash table and start clearing it out again. You basically have to do a rehash or nuke the hash table and just repopulate it again, because it might come from stuff that's in an array, and the hash table is used as a way to, as a quick lookup, right? So maybe, yeah. So that's fine. Is there anything interesting we can do? Anything else we can do is interesting? Yeah, there's not much I can do without sort of like playing around, like any of these speed up things that we could do, like playing around with this, right? How much do we like when you finish looking in a bucket, should we skip to like so many buckets ahead? And can we play around how this works? Because I've heard an interesting idea where maybe you could skip based on the hash. Right, basically have a bit of a, you take some bits out of the hash and you sort of like skip that many buckets, and that helps avoid you know, there's two different types of collisions, right? There's a hash collision, but there's also a collision on the bucket. But there's a collision on the bucket, so that avoids, if you skip the bucket in a different way, it avoids that collision being the same. But yeah, I can't really play around with that until I actually have any data. Right, see you there, Rohan. Good to see you. About 3 in the morning here. Right. Oh, hope you get good sleep. I'll see you in the next one. Have a good rest of your week. Awesome. Good to see you, Laurie. Thank you. Thank you. An example: you have 16 buckets in your values, and you're setting 16, whatever, and all of them end up being in the same. They'll end up being the same bucket. Basically, the same as if your hashes were. Basically, the same if all your hashes would be multiples of the prime bucket count, which is less likely. Right, I see. The only way of doing it would be by skipping either primes. You'll ignore certain buckets, I see, because they're just grouping buckets, wouldn't it? Hmm. Yeah, that's interesting. See, so how easy it is to do the prime thing? Do you have to do like you have to do a prime table, isn't it? And just find the nearest one in the prime table, because calculating primes is just too expensive, isn't it? So you'll just search through the prime table until you find something that matches, right? The prime tables get quite big, don't they? List of prime numbers. Yes, obviously you'll probably skip all the low ones anyway. You'll probably skip all the low ones and just be like, okay, we'll start from like 1024 and above, whatever the nearest prime is from there, right? Because none of them below here are probably practical. But you have to. Oh, there's so many primes. Maybe you'll skip a bunch of primes as well. You'll do like. In general, if you look at the first n prime number, it's probably first n prime as possible bucket counts. You only look at the first n. at a certain point, the number of buckets makes no sense. Hmm. Right, I see. Yeah. Yeah, maybe you can sort of skip some of these as well, because maybe you sort of define your own table and just search through it. Yeah, it's interesting. Well, the other thing was like, do you do a linear? So you can't skip over them. Right. Okay. I think that's pretty decent place to kind of say that this hash table is basically good enough to use. We just need to really get something using it before we can really test to see if it's, you know, tweak it to make it even better than it is. But the interface is there, so we can actually start using it now. Did I forget something from last stream that I remembered earlier? There was something from last stream to do with the allocator, maybe. Oh yeah. Whenever we reset the linear allocator, we didn't zero the memory because we kind of want to make it be zeroed by default, I think. So maybe when you set the cursor back, I'm thinking what we should be doing is that cursor has to be less than cursor. So you can only restore it back. New cursor must come before old cursor. P. Something like that. And then what we want to say is cursor, cursor. Cool. And then we just want to say memset. Memset from, okay, 0. Let's do memset from cursor to wait, 0 to 0. Let's do the bigger, take the smaller. There we go. So now it always gives zeroed memory. Good to know. Unless you really need it, I would limit it around 4K buckets. That's already a bit extreme. Yeah, but my buckets are quite small. Right. My bucket's like 8. So you're saying like 4K times 8. I say 0x00 because it's to emphasize that they only use a byte. Because the prototype of memset is an int. So I just emphasize when people read it that it sets a byte at a time. But that's just my style, is all. Awesome. So let's go ahead and get this guy. Let's just make sure it still runs. The game still runs. Bam. Such a good game. Let's commit that. So this is like, add hash table. So we've got a nice hash table now in the code base. Let's push that up to the all my days I just remembered. We've got to pull and merge the Windows changes. Right. Oh yeah. I think that's still fine. Right, git pull dash dash tags. Let's get that day 11 tag back, bam. So pushing the changes up to the repo. Then we're going to do a nice git tag to say day 12. Then we are going to say push origin tags. We should have a day 12 tag on the repo as well. Come on. Would clobber existing tag clobber my existing tag? Oh, I need to say git tag dash d day 11. I need to pull their 11 in and then push my 12 up. Oh yeah. Cool. So yeah, for those who have access to the code, if you're a Twitch subscriber, you can hop on Discord, get access to the code. Also, if you want to support me more instead of Twitch, you can support via Ko-Fi, which is, if you look in the About page down below, you'll be able to see exactly how to do that, or just by following this link here to the Discord. There's some information about that there. Yeah, bucket sizes also influence the decision of the max bucket counts a lot. Yeah. Can't wait for the upcoming DLC that inverts the triangle. Oh yeah. Yeah. I'm sorry, but that's gonna be a paid DLC. Oh no, a joke. Right. Yeah, so next stream is gonna be really good. So we're still working on one more collection, and it's going to be the object pool. Another name is like a slot map. Basically, it's just an array. It's a superset of an array, which allows you to allocate an element out of it. So basically, and we'll go over this in so many more details, exactly how it works. But imagine if you have an array of entities or something like this. And it's a way of like basically saying, hey, you just say to the object pool, can I have an entity? And it gives you back a slot to the entity. And then you can say later on, like imagine you've allocated like this slot, that slot. You can then just say, hey, can I free this slot here? And it will just free it. So it's a way to allocate and free individual elements of an array, and also keep track of use after freeze, and when something has been freed more than once, because you basically use handles or IDs, as we call them, instead of pointers. So when you refer to this element here, you basically refer to it via an index and a generation counter. And this is basically a smart index. Yeah. Basically, rather than having smart pointers, you have smart indices. This is it. They're legendary. It means you can basically like serialize these buggers out. You get checking for use after freeze and all of that jazz. Yeah, it's really cool. Pools are amazing. They're amazing. They're quick. You can quick to allocate things. The only problem with them is you can't iterate over the elements super fast, but it's possible for debugging code, so we're going to put it in anyway. But yeah, these are really cool. We're doing these next stream. So yeah, keep an eye out for that one. And also ignore my stupid message about 4K being the largest bucket count. My brain was screwing up. No worries. No worries. I wasn't taking that as a solid thing. But yeah, thank you for the other advice. It was really good. Appreciate it. But yeah, next stream is Thursday, 6:30 p.m. GMT +1. So, let's find somebody to raid. There's somebody, and it's amazing. Right. Send Jessica raid here, because she's working on her own custom game. I think she has a custom engine as well. Yeah, no, she has a custom engine, but I think she does it per game. I'm not sure. Maybe she does. We'll see. But yeah, thanks for coming, everyone. It's really cool. Lots of good stuff today. Got a hash table done, and we can actually start using it whenever we need it. If load factor between 0.8 0.7 0.8 with 8 buckets, you store around 21 to 27 items in the table, etc. Right. Yep. Right. Have a good rest of your week. I'll see you. Well, no, have a good tomorrow. I'll see you Thursday. Bye.